Welcome to today's talk, and we are beginning Chapter 18. Chapter 18 has to do with gas transport in the body. As I'm speaking to you right now, I'm taking in gases with, of course, the concept we talked about in Chapter 17. Expanding the lungs, gases go in, contract, and then gases go out. And what's interesting is that the gases that come into the lungs that are inhaled are mainly oxygen rich. And the gases that come out are carbon dioxide rich. So what you have to think about is every time you inhale and exhale, you are basically, the composition of gases is completely different. And that's because it is being exchanged in your body, which if you think about it is pretty awesome. So how exactly does that happen? Well, let's go ahead and draw a diagram here. So we're on chapter 17, gases and how they diffuse down concentration gradients or partial pressure gradients. So gases diffuse, and now let's do partial pressure gradients. So let's draw some environments here. We have here the alveoli. We're only drawing the alveoli because they are the functional units of the lungs. Actually, drawing that in blue is a really bad idea. We're going to draw it in pink. It's a bad idea because, well, I was planning on drawing deoxygenated blood as blue. And we are now going to have here arterial blood. And then we are going to have body cells. Actually, let me finish drawing the arterial blood here. We have body cells, which I'll draw here in green. And these body cells, keep in mind that we have 60 trillion odd cells. These body cells, what they're going to do is they are going to take oxygen and put in carbon dioxide. But I'll draw that in a moment. So slowly, the blood is going to become more and more deoxygenated. I'll draw this in purple just as a token means to show you the transition. And then we're fully on to deoxygenated blood. So draw here in blue. Then we're back here to the alveolus. So this is kind of our loop here. So we know that oxygen in the atmosphere, and we'll do oxygen in black. So I'm not actually going to keep on drawing O2. This will make it easier. So what we are going to do is we are going to say that O2 is going to be in black. We'll say CO2 is going to be in orange. So the partial pressure of oxygen in the atmosphere we know is about 160 millimeters of mercury. And carbon dioxide we know is a lot smaller, 0.25 millimeters of mercury. Now oxygen in the alveoli is equivalent to 100 millimeters of mercury. And carbon dioxide, though, is quite a bit higher. That's 40 millimeters of mercury. So we know that under normal conditions, oxygen is going to diffuse into the alveoli. And carbon dioxide is going to diffuse out of the alveoli. But of course, it's a bit more complicated than that because we know that in the arterial blood, or sorry, we will know that. The arterial blood is going to have the equivalent of 100 millimeters of mercury, of oxygen, and it's going to have 40 millimeters of mercury of carbon dioxide. Now, why is that? Well, gases, they diffuse passively. Gases also go down their own, what we call a partial pressure gradient. Now, the oxygen pressure in the alveoli is 100. The carbon dioxide pressure is going to be 40. Because of that, the gases in the alveoli are going to diffuse in the blood until they reach equilibrium. So at this point here, the oxygen concentration in the blood is going to equal the oxygen concentration in the alveoli. So it has reached equilibrium. And I'm going to erase this because it's going to clutter our diagram. Now let's kind of see our loop here. Oh, and also the carbon dioxide concentration is 40 in the alveoli and the blood because the same exact reason, but it will make more sense as we go around the loop. Now here we have the body cells. And body cells are constantly taking oxygen from the blood, which will indicate with the black arrow, and they're constantly expelling carbon dioxide, which I will put here in the green arrow. And the more that our body does this, the more that our cells do this, then the more deoxygenated the blood is going to get. Because oxygen is going away, but then at the same time, carbon dioxide is going into the blood, and eventually the blood is going to become deoxygenated. What's going to happen is that in the venous side of the circulation, and I'm going to go outside the loop here just to make it less cluttered. In the venous blood, oxygen is going to be less than 40 millimeters of mercury, and carbon dioxide is going to be greater than 46 millimeters of mercury, which makes sense, right? It makes sense because when the blood is fully oxygenated, it's very rich in oxygen and very poor in carbon dioxide. Well, not very poor, but lesser in carbon dioxide. As it goes through our body cells, we are going to have significantly reduced oxygen content because the cells have taken it, and we are going to have significantly increased carbon dioxide concentration because the body cells are putting that back into the blood. Now, obviously, that's not ideal. So what's going to happen is that when we get back to the alveoli, so I'm going to draw this, we have 46. That's going to diffuse into the alveoli because the carbon dioxide concentration in the venous blood is higher than the carbon dioxide concentration in the alveoli. And it's going to diffuse until it reaches equilibrium at 40 millimeters of mercury. And oxygen, of course, is going to go into the blood because now the oxygen is going to be significantly deoxygenated. We see that it's less than 40. So we have here two partial pressure gradients. So an easy way to think about it, which isn't 100% accurate, but it's good as a learning tool. Think of the alveoli always has 100 millimeters of mercury of oxygen and 40 millimeters of carbon dioxide in the alveoli. It is continuous. It is always. Now, when the blood passes through the alveoli, it's always going to reach equilibrium with the conditions in the alveoli. So oxygen is going to diffuse into the blood until the partial pressure gradients have reached equilibrium. Same with carbon dioxide. So oxygen is going to diffuse into the blood until both environments have 100 millimeters of mercury of oxygen, and carbon dioxide is going to diffuse out of the blood into the alveoli until they've matched at 40 millimeters of mercury of carbon dioxide. The gases will always diffuse until equilibrium is reached because gas exchange or gas movement is always passive. It cannot be active. So it's always going to diffuse until it reaches equilibrium. And the cells, I'd be remiss if I didn't do the cellular environment. Cells are constantly using oxygen because of cellular respiration. That's how they make energy. And they're always expelling carbon dioxide. So the cells are always going to be very oxygen poor and very carbon dioxide rich, but you want that. You want that because it means that they're working optimally. And the answer to the questions on the bottom is, as I explained earlier, is assume that the gases in the alveoli are always going to be 100 millimeters of mercury of oxygen, always 40 millimeters of mercury of carbon dioxide, and the environment in the blood will reach equilibrium with those values, but never more, because gas diffusion will stop when both environments have reached equilibrium. Hopefully I was able to explain that well enough. If not, we can go over it during the hours of the office. And the reason why blood loses oxygen is because of cells. Okay, so now we're going to move on to, so what are some factors that affect gas exchange in the body? Well, there's lots of factors, but the lungs are the one thing, especially the alveoli, that you want to make sure are incredibly healthy. Because think about it, if I were to tell you to stop breathing for a minute, just a minute, hold your breath, likely be very catastrophic to your body. Even though you can train it, it certainly is not ideal, because if you stop respirating, carbon dioxide will build up in your body, oxygen will be significantly depleted, and you might suffer some effects of hypoxia. So this is definitely one part of your body that you want to keep healthy, and that's why COVID-19 is such a scary disease, because it targets the one thing that you really do not want it to target, which is the alveoli. But anyways, what are some factors that affect gas exchange in the alveoli? Okay, well, the first is the composition of the inspired air. As we talked about, is we assume, or we use as a baseline for the composition of inspired air, a value of 760 millimeters of mercury, and that is the atmospheric pressure at sea level. However, you can also have environments where there's reduced O2, and maybe even some that are significantly reduced in O2. Also, if you do something which is not very wise, but if you do something called breathing into a paper bag, you can also have some air that is higher in CO2, has a higher partial pressure of CO2. If you exercise in a gym, especially the group classes, guarantee you the composition of the inspired air, if it is not well circulated, it's going to be significantly higher in carbon dioxide. Okay, so that's the composition of inspired air. Now the next one is going to be perfusion. And perfusion is just assuming that there is adequate blood flow going to the alveoli. So adequate blood flow to alveoli. Next is going to be surface area. So the alveoli, if you were to take them all and flatten them on the ground like pancakes, they would take up about 700-ish square feet, 750 square feet. So it's about the size of a large hotel room, about the size of a, I don't know, hotels. They have like the standard rooms and like the slightly upgraded ones that have a token couch. It's like the size of the slightly upgraded one with a token couch. But surface area is basically the amount of space that gases have to diffuse. You want a lot of surface area for gas diffusion. So there's some conditions that can damage or destroy alveoli. And those are conditions that can reduce surface area. Again, that's what's scary about COVID-19, is it results in a possibly in a condition called alveolar consolidation, where the alveoli fill with fluid and cannot diffuse gases, which reduces the surface area possible for gas exchange. And the next one, and this one is also very important, is distance. So fibrotic alveoli, meaning that they're thickened with additional tissue, and for pulmonary edema, can increase distance. Now, this isn't good because it means that if there are thicker alveoli, so this is a normal alveolus, and this is a thickened one, you'll see that the thickened one, there's more space needed for diffusion. And also, this is the blood distance in a normal person. This could be one of someone that has pulmonary edema, meaning that there's going to be more fluid for the gases to get through. Okay, well, speaking of that, we're going to talk about hypoxias now. Now we're going to talk about types of hypoxias. And the first one we're going to talk about, oh, by the way, hypoxia is any condition that results in oxygen deprivation. Sorry, I know that looks like graffiti, but that does indeed say hypoxia. So what determines proper diffusion rate? Well, diffusion is a property of the following. So it is surface area, and I'm not going to have you do any calculations, don't worry about that. It is surface area combined with barrier permeability, meaning how permeable are the alveoli, and also it is going to be distance. So these are the three factors that affect gas diffusion. And surface area is basically, to kind of put that in plain English for us, surface area is going to be number of alveoli. I should say functional alveoli, but you get the idea. Barrier permeability, alveoli thickness, and distance has to do with edema. That's the main thing that can increase distance. Now, the first one we're going to talk about is a condition called emphysema. And this is a common condition for people that live in either highly polluted environments, worked laborious jobs involving indoor mining or asbestos factories, or smoking. So that happens is that, let's say that a healthy person is going to have, I'll just say, 10,000 alveoli. And let's say that someone that is diseased with emphysema, they're going to have 7,500 alveoli. So what has happened is that they've significantly reduced the amount of surface area available for gas diffusion. Thus, they could become hypoxic just because they don't have enough functional units of gas exchange. Now, what is a therapy for that? Well, recall that, and I don't know how much I mentioned this in the last chapter, but water vapor displaces gases, meaning it becomes a part of the gas mixture, but it is not a gas that we can use for oxygenation. So one possibility is to move to a drier climate because that could increase oxygen saturation. The other is to give supplemental oxygen. If you increase the partial pressure gradient, as in you have you enrich the environment with oxygen by giving yourself additional oxygen, it's going to increase the partial pressure gradient, meaning more oxygen will diffuse into the alveoli, maximizing the alveoli that you do have. Next is going to be fibrotic lung disease. Fibrotic lung disease. And the word that you are looking for there is thicker alveolar layer. So fibrotic lung disease, what's going to happen here is that this is going to be a normal alveoli, as I drew earlier, and this is going to be one that is diseased. So you're seeing that it's a little bit thicker. And that is going to create a hypoxic situation because we've increased the barrier, or we've decreased the barrier permeability. Next is going to be pulmonary edema. And this is usually caused, it is a symptom of cardiovascular failure or cardiac failure. So what happens and this is the unfortunate part of a summer course, is we just don't have enough time to talk about everything. But we rely on a properly functioning heart in order not only to pump blood, but also to keep it moving. And if blood does not move through our body well enough or fast enough, then it gives the plasma, the liquid in our blood, time to kind of diffuse out of the capillaries and drain back into the body very slowly. So pulmonary edema is a consequence of, as they call, heart failure. But anyways, what's going to happen is that you are going to increase the distance. So this is going to be a normal alveoli, normal blood supply. This is going to be pulmonary edema. The alveoli themselves are going to be healthy, but the distance needed to diffuse to the blood is going to be increased. And the last one here is going to be asthma. Asthma is a very common condition. But what happens is that under times of stress, or maybe just randomly, is the bronchioles are going to bronchoconstrict. So asthma, this is going to be a normal alveoli. This is going to be one that is of a person having an asthmatic attack. So you're going to see that the radius of the bronchioles is going to be significantly reduced, which can create a hypoxic situation because gases are not able to get into the alveoli. All right, right on. Okay, so now we're going to talk about gas transport in the blood. Gas transport in blood. So red blood cells are designed to maximize surface area. And we know that because they have a biconcave shape. So this is what a red blood cell looks like from the side. So the reason why it has this dip here is to maximize surface area. Red blood cells have no nucleus, no membrane-bound organelles. In fact, they're not even really cells. And they also have, they can't even perform cellular respiration. Instead, they perform anaerobic respiration. Anaerobic respiration, meaning that they make energy without oxygen. And these basically are bags filled with a protein called hemoglobin. Millions of hemoglobin proteins are stored here. So basically, and this is going to sound derogatory, but they are bags of hemoglobin. Bags of hemoglobin. Okay, so let's go and look at a molecule of hemoglobin. And what we are going to see here is that there are two types of subunits in adults, alpha and beta subunits. For the intensive purposes of this course, they're basically the same. So these are the subunits. So this is a hemoglobin molecule, just one. Protein is more appropriate, right? Hemoglobin protein. So we have the subunits, but then in the center, we are going to have a molecule of iron, which is Fe plus, or sorry, Fe2 plus. Okay, now oxygen is going to bind reversibly to the iron group, like so. Now when oxygen binds with hemoglobin, we call it oxyhemoglobin. And keep in mind that, at least the way that I put it, is hemoglobin begrudgingly binds with oxygen. Really is not a friendly fit because the hemoglobin itself has to change form. So it binds with oxygen, but it doesn't exactly do so happily. Carbon dioxide is also transported on the via hemoglobin, but differently. Carbon dioxide, which I'll draw here in bright green, actually binds with the hemoglobin subunits. And when this happens, when we take CO2 and combine it with hemoglobin, we are going to get something called CARB, or carbon dioxide, amine O hemoglobin. Carb amino hemoglobin. So they're both they both travel, or they're both transported via hemoglobin. It's just that carbon dioxide binds with the subunit, and oxygen binds with the iron atom, and both these processes are reversible. Now, here's something to keep in mind why hemoglobin is so necessary. So I'm going to draw here two environments. They are two beakers. Now one is going to have, okay, they're both going to have water. And one is going to involve oxygen, and the other is going to involve carbon dioxide. So one container we are going to give oxygen, and the other we're going to have carbon dioxide. Now first, let's infuse this beaker of water with oxygen, which I'll draw here in sky blue. What's going to happen is this. It's going to go into the water, and it's going to form bubbles. And most of those bubbles are going to come right back out. Just like this. In fact, only about 2% of O2 dissolves in water. Now, why is that? Well, water is a polar molecule. Oxygen is a nonpolar molecule. Because of that, they don't mix well. It's also why if many of you guys have aquariums, it's important that you monitor the fish. Okay, if you have an aquarium, you're probably like, okay, idiot, but I don't take care of pets. Every year, I don't know why, but every year, a student or a former student comes with a fish tank and gives me fish. I don't want the fish. I can barely take care of myself, let alone an animal. So many times, oh, okay, maybe a couple times, I've noticed the fish swimming very close to the surface. And I'm like, well, that's odd. Maybe they just are cold and want some sun. I'm not a fish guy, okay? I'm a molecular cellular biologist, not an ecologist. Ecologists, I wish them the best of luck. They love what they do. For me, a fish is just an animal. But anyways, I'm like, oh, maybe they're cold. Logical thinking, right? Well, it turns out they were actually oxygen deprived. Because if you feed the fish too much, which my students are very concerned that the fish are going to starve because teenagers, they're always starving. So they're afraid so they think the fish are always starving. So they overfeed the fish. And what happens is that the excess food is actually consumed by bacteria. And bacteria, many of them are aerobic bacteria. And if you have a bunch of bacteria stealing oxygen from the water, it's not going to leave enough for the fish. So basically, my fish tank becomes a bacteria tank. Now, it's interesting because you think, well, the water is sitting in an oxygenated room. True, but very little of the oxygen, as we can see, actually gets dissolved into the water. In fact, that's actually a big concern right now with dumping so much sewage and waste into the oceans. It is actually causing bacteria overgrowth and creating something called oceanic dead zones, which are really eerie. If you have time, I suggest you Google it and check it out. CO2, on the other hand, is polar. And I'm not sure exactly how much dissolves, but most of it dissolves. Most dissolves plus reacts in H2O. So what happens is that CO2 plus H2O is going to form H2CO3, which is going to be carbonic acid. This is actually why we have acidification of the oceans, because since we're putting more carbon dioxide into the atmosphere, it is reacting with water, and it's actually making water more acidic, which is having drastic effects on the local ecosystems. So if we did not have something that could better bind to oxygen, then there's no way that the oxygen from the alveoli could properly diffuse in the blood plasma. We would not have nearly enough to meet our needs, which is why it's really important that we have a molecule that can do it for us. All right, and part 2 is coming up shortly. All right, so we continue down our journey. And we're going to talk about steps of O2 transport in blood. And this is going to be a pretty straightforward process here, luckily for you. We're going to have an environment. We are going to have body cells. And this is going to be one of the most straightforward things you learn all year. But the red blood cell is going to carry on it oxygen. And what's going to happen is that as it passes through the blood and toward the body cells, oxygen is going to disassociate from the red blood cell. It's going to go into the body cell. Yep, that's it. Pretty easy. So steps of O2 transport is oxygen is going to be onto the red blood cell, the erythrocyte, as it's properly called. As it gets near the deoxygenated cells, oxygen is going to disassociate from hemoglobin And what's going to happen is that HbO2 is going to become Hb plus O2, and the oxygen is going to go into the cells. Now you're going to see here on the bottom principles related to oxygen transport. And mainly, I want you to focus on law of mass action, which is interesting. And one thing that I compare it to is, in a way, following the leader, so to speak. So law of mass action. And I'll tell you a story. So when I was student teaching, I was teaching in a class, English language development. Once upon a time, I was an English major, and when I got my teaching credential, I actually got it in dual English and biology. For my student teaching, I was placed in an English as a second language classroom. Most challenging teaching assignment I've had because, one, I was new and didn't know what I was doing, and two, it was English language development, so I was dealing with students of various English levels. Proficiency, excuse me. So I was really excited about this book called The Open Window, and I forget exactly what it was about, but it had a pretty cool twist. But it was written on a 4th grade level, so I'm all excited, and we're taking turns reading the story, and all of a sudden, one student gets up and leaves. Then his friend in the class gets up and leaves. Then the girl that had a crush on the first boy that left, she got up and left, until the entire class got up and left and just walked out. And of course, I'm like freaking out. I go outside and make every empty threat in the world about calling parents and principal. And then the one boy came back, and then his friend followed, and then the girl that had a crush on the first boy followed back. But that's an example of law of mass action. It is more or less, if something begins to leave, then others will follow it. So the equation here looks like this. Hb plus O2 equals HbO2. But the same thing can also happen in reverse. We call this shifting to the right or shifting to the left. So basically what this means is that with the law of mass action, if the red blood cell is in an environment where there's lots of oxygen, mainly at the site of the alveoli, what's going to happen is that via the law of mass action, since there's so much oxygen, more oxygen is going to bind with hemoglobin. And the curve is going to shift to the right. However, once the red blood cell gets to the body cells, we are going to see here that the cells are environments that have very, very little oxygen, and they need it. So via the law of mass action, the more oxygen leaves, then the more oxygen will follow it. And in this case, the curve will shift to the left. So it goes like this simply. The more oxygen binds with hemoglobin, the more that will continue to bind. And the more oxygen disassociates from hemoglobin, then the more will follow it. That's the law of mass action. The rest of these equations, just note them, but you're not going to be tested on them. But it is interesting to take note of them. All right, so what are some factors that determine oxygen and hemoglobin binding? Well, mainly it's going to be, and I'm not going to write this down, but it's going to be partial pressure of the PO2 of plasma. Of course, the more oxygen is perfused in the alveoli, the more we'll get into the plasma. and then the more oxygen will be available for binding. And also, you do need plenty of hemoglobin because you need plenty of binding sites. That's also why the condition anemia is so dangerous for proper functioning, because you have fewer erythrocytes and fewer molecules of hemoglobin for oxygen binding. Oxygen binding is going so this will show you. This is a normal person, and this is a person who is anemic. What's going to happen is someone that has a normal physiology, they are going to have plenty of red blood cells. And recall that red blood cells can bind with up to 4 molecules of oxygen each. This is good because there's plenty of binding sites for oxygen. The problem with the anemic person is that we have a reduction in red blood cells. What's going to happen is that there's fewer. And because there's fewer, there's going to be fewer binding sites for oxygen, meaning it's going to be depleted a lot faster. Oxygen is expressed as a percentage, and a healthy person has an oxygen saturation of about 98%. This can actually be detected through, I believe, a device that kind of acts as a spectrophotometer. It can actually measure the amount of oxygen that is contained in the hemoglobin molecules. At any one time, one molecule of one red blood cell should have 98% of its hemoglobin fully saturated with 4 molecules of oxygen. Means that 98% of the hemoglobin molecules in one red blood cell are going to be saturated with 4 molecules of oxygen. 98% of them, which is amazing, and it's a testament to just how well oxygen can bind to hemoglobin. All right, so when we come back, we are going to talk about factors affecting oxygen binding. Okay, well, I thought I paused the recording. Turns out I did not. So we're just going to roll with it. All right, so go ahead and look at this graph here. It's called Binding Properties of Hemoglobin. And we see here that on the y-axis, we are going to do the partial pressure of oxygen available in the alveoli. And on the y-axis, we are going to have hemoglobin saturation. And of course, this is going to be identified in a laboratory. This really cannot be determined in vivo. And if we look here, no, come back. And if we look here, it's going to have a curve like this. So the great thing about hemoglobin's ability to bind oxygen is that even in low partial pressures, it can bind a significant amount of hemoglobin. In fact, at a partial pressure of just 40 millimeters of mercury, you can have 80% of the hemoglobin contained in one red blood cell fully saturated. And we see that as you increase the partial pressure, then it's going to slowly increase until it reaches saturation, which is 100 millimeters of mercury. Now, once you get to about a partial pressure of 80 millimeters of mercury, it's basically maxed out at 90-something%. Further increases in oxygen partial pressure is not going to have an appreciable difference in hemoglobin saturation. And max is about 98%. I believe I read somewhere that if you wanted a full 100% saturation, you need a partial pressure of oxygen around something insane like 400. Now, there are also factors that affect binding properties, and those are going to be interesting. I really wish this would stop disappearing. No, I don't want, no, I do not want this. No, and now it's not going to, oh my gosh, that is annoying. I had this so well organized too. Okay, anyways, here we are. So I'm just gonna do 100, 90, 80, 70, 60, 50, 40, 30, 20, 10, 0. Okay, anyways, so now we're going to have factors influencing HB affinity O2. Sorry for the sloppy writing, but it's on the outline. And the first one is going to be pH. Actually, let me erase this. It's painful looking at it. All right, so first one is going to be the effect of pH on oxygen binding, or hemoglobin affinity for O2. Now let's talk about pH. Now the reference range is going to be a pH of 7.4. And it's going to look like this. This is not an exact value, it's more of just to show a concept. So red is going to be a pH of 7.4. Now what happens if we increase the pH of the blood? Well, it's going to look like this. And I'll explain what this means in a bit. This is 7.6 according to the graph in the book. This is on, I believe, figure, it's on the outline, but it's figure, yeah, it's on the outline. I can't see on my diagram here. All right, now what if we decrease the pH? What if we go with instead a pH of 7.2? Well, the curve is going to shift to the right, as they say, and oxygen is going to be less, or hemoglobin's affinity for oxygen is going to be even less. So what does this mean here? So red is our baseline, it's our comparison point. If pH is high, oxygen is going to be more likely to stay bound to hemoglobin. Because if the pH is high, that means that the metabolic activities of the cells are lower. Because we talked about that carbon dioxide reacts with water to form carbonic acid. And that really only happens if the cells are working in overtime. Now, a pH of 7.2 assumes that the cells are in a state of increased activity. Therefore, the hemoglobin proteins, which really prefer to hold on to oxygen just in case it needs it all of a sudden, has suddenly found that it needs it all of a sudden. So what's going to happen here is that oxygen is going to be more likely to disassociate from hemoglobin to meet the metabolic demands of the cells. So that's why with a lower pH, the curve shifts to the right, and with a higher pH, it shifts to the left. Higher pH means that oxygen is more likely to stay bound to hemoglobin. Lower pH means oxygen is more likely to disassociate from hemoglobin and go toward the cells. Next is going to be the effect of temperature. Let's go ahead and get this out of the way. Okay, so now we have the effect of temperature. And we're going to have some temperatures here. And our baseline temperature is going to be about body heat, or a normal body temperature, about 37 degrees Celsius. Now what happens if you decrease the temperature? Well, the curve is going to shift to the left significantly. So this is going to be 20 degrees Celsius. Red is going to be 37 degrees Celsius. And then in green, we're going to have 43 degrees Celsius, and the curve is going to shift to the right. Now, why is this? Well, it has to do with a couple of factors. The first is that colder weather makes chemical reactions happen more slowly. Also, when the human body is exposed to lower temperatures, in addition to having reduced metabolic activity, that also means that the cells are in a lower state of activity. So it's a combination of two things. Colder weather slows down chemical reactions and also metabolic activity. Now, higher temperatures, recall that heat makes things react faster. And on top of that, when does the body generate a lot of heat? During exercise. Therefore, when temperature increases, oxygen is more likely to disassociate from hemoglobin and go to the cells. So when it's colder, oxygen is more likely to stay bound to hemoglobin. And when it gets hotter, then oxygen is more likely to disassociate from hemoglobin and go toward the cells. Next is going to be the partial pressures of CO2. And CO2, as we'll find out, is actually the largest determinant of rate respiration as well. So we are going to have our baseline is going to be red. It's going to be a PCO2 of 40. But also when it gets when the concentration of CO2 reduces, say 20, and then in green we're going to have 80, which is pretty significant. Okay, so this is our baseline here. Now, when the partial pressure of CO2 in the blood is lower, the curve is going to shift to the left, and oxygen is going to be more likely to stay bound to hemoglobin. However, when the partial pressure of CO2 in the blood increases, that means that oxygen is more likely to disassociate from hemoglobin and go toward the cells. Why is this? Well, for starters, the amount of CO2 in the blood is determined by the metabolic activity of the cells. If the cells are in a lower state of activity, that means they don't need as much oxygen. If they don't need as much oxygen, then oxygen is going to stay bound to hemoglobin until it's needed. However, when the partial pressure of CO2 goes up, that means the cells are in a state of increased metabolic activity. As a result, they need more oxygen, and they're also expelling more carbon dioxide. Therefore, when carbon dioxide is higher, that's a signal to the red blood cells that they need oxygen. And when the partial pressure of CO2 is higher, oxygen is more likely to disassociate from hemoglobin. Lower CO2 is going to result in increased hemoglobin affinity for oxygen. Increased partial pressure of CO2 is going to result in increased dissociation of O2 from hemoglobin. Now, next is going to be a compound that is secreted when someone is exposed to higher elevations, and it is called 2,3-BPG. It's a compound that is secreted when somebody is in higher elevations. So normal 2,3-BPG is going to look like this. Why did I do that? Come back. There we go. My poor graph is getting decimated. All right, it's going to look like this. Now, if there is no 2,3-BPG in the environment, so this is no, and this is normal, then it is going to look like this. If there is no 2,3-BPG, curve will shift to the left. However, if you add it, the curve is going to shift to the right like this. So what this means is that this compound, the more 2,3-BPG is present, I just wrote 2B, BPG. The more 2,3-BPG is present, then the more likely oxygen is to disassociate from hemoglobin. Less 2,3-BPG means that oxygen is more likely to stay bound to O2. More 2,3-BPG means that oxygen is more likely to disassociate from O2 and go to the cells. This makes sense that it will be secreted when someone is in increased elevation, because that means that their cells need more oxygen. So what it does is that it is going to make it easier for oxygen to disassociate from hemoglobin and go toward the body cells. These are factors that affect oxygen hemoglobin binding. Very important that you know the conditions that will cause the curve to either shift to the left or to the right. You want to view this diagram. It is your constitutional right, and it is figure 18.9. Know this really well. I suggest that you actually draw out these graphs yourself. So keep in mind that when I say the curve shifts to the right, that means oxygen is more likely to disassociate from hemoglobin and go toward the cells. When I say the curve shifts to the left, of course, the red line is always our baseline. When the curve shifts to the left, that means that oxygen is more likely to stay bound to hemoglobin and not go to the cells. All right, everyone. Well, welcome to your, what's this? Optimize screen share for video clip. Let's try it out. All right, anyways, so you may remember me talking about how easy and straightforward oxygen disassociation to body cells actually is that the blood cell gets near a cell, oxygen disassociates. Easy. It's much easier to make a mess as it is to clean it up, as they say. So we're going to talk about cleaning up the mess, steps of CO2 transport. And it's very important that you understand this diagram really well because there's always a free response question on it. No ifs, ands, or buts. So I'm going to draw here in environment and make it pretty big. Okay, now it's my cue to get off the screen. And over here, we are going to have body cells. So I'll go ahead and draw here in a nice, rich green color. And I'm not going to write down the steps because they're going to be on your outline, but I will mention them. All right, so the first is that we know that cells are constantly putting CO2 into the bloodstream. And that has three fates. One of those fates is that CO2 is going to be dissolved in plasma. Over time, it's going to react with water, and it is going to dissolve. It's going to dissolve in H2O. So CO2 plus H2O in this case is going to turn into dissolved CO2. And how much of that gets dissolved? 7%. So about 7% of carbon dioxide is transported in the blood plasma. Now, what about the other 93%? Well, that's where the red blood cells come in handy, specifically hemoglobin. All right, so 20% of carbon dioxide is actually going to be bound to the subunits on the hemoglobin protein. Carbon dioxide plus hemoglobin, as we know, is going to form carb amino hemoglobin, abbreviated CO2HB. That's going to make up about 25% of all carbon dioxide transported. The third one, we need to get a bit creative here because there's not enough hemoglobin subunits to transport all the carbon dioxide released by the cells. So to get a bit creative here, what's going to happen is that we are going to take the CO2 plus H2O reaction, and using an enzyme called carbonic anhydrase, CA, and I'll write that here on the side, carbonic anhydrase. What's going to happen is that you are going to get H plus, and then H plus, and then you are going to get HCO3 minus, that is bicarbonate. So the proton is actually going to be bound to hemoglobin, and we are going to have HBH, which we can do in large quantities because a proton is a very small thing. Now, what's going to happen to the bicarbonate? Well, what's going to happen is that bicarbonate is actually going to be put back into the blood, so it can travel along in the plasma. However, very important is we can't just add negatively charged molecules to the blood, because that will make the entire plasma, that would make it very negatively charged. So what we're going to do is we're going to send out this rather large large molecule, and instead we're going to bring in a single chlorine or chloride, going to have a net charge of a negative. So this is going to be called the chloride shift, and it's very important because it is a way of balancing charges. You are going to exchange one negatively charged molecule, which is a bit larger in bicarbonate, HCO3-, and you are going to shift it for chlorine, which is going to have the same one negative charge, but it's going to be a lot smaller. So once again, about 7% of carbon dioxide is going to be dissolved in the plasma. About 25% is going to be bound to hemoglobin as carb-aminohemoglobin, and it's going to be carried on to subunits. However, the remaining 70% we need to be a bit creative with, just because space is limited in the red blood cell, is you are going to take carbon dioxide and water, and you're going to speed up the reaction with an enzyme called carbonic anhydrase. Ultimately, that's going to create a proton in the form of a hydrogen, of course, and HCO3-, which is bicarbonate. So we can neutralize the proton by binding it with hemoglobin to make HBH. And then the bicarbonate, we can put that back into the blood and shift it with a chlorine molecule atom. What that's going to do is it's going to allow us to balance charges. We're putting in the larger bicarbonate into the blood. Now, what's going to happen now is that eventually this red blood cell is going to get to the alveoli. Going to get to the alveoli. And now the environment is going to look like this. So this here is going to be the alveoli. And what's going to happen is that that's 7% of CO2, which I'll put here in red. The 7% of CO2 that's dissolved is just going to diffuse into the alveoli. Easy. The 25%, which I'll do here in sky blue, that was bound as carb-aminohemoglobin. Due to the law of mass action, carbon dioxide is going to dissociate from hemoglobin, and it's eventually going to go into the alveoli. Now, what about the bicarbonate, which I'll put here in green? What's going to happen is the reaction is going to reverse. Bicarbonate is going to go back into the red blood cell, and it's going to do a reverse chloride shift. So bicarbonate is going to go back into the red blood cell, and chlorine is going to be substituted out. So we are going to have a reverse chloride shift. Then what's going to happen is that the proton that was bound to hemoglobin is going to disassociate. We are going to have this, and then we are going to have a reversal. So what we are going to have here is we are going to have bicarbonate, HCO3- plus H is going to equal CO2 plus H2O, and the carbon dioxide is going to diffuse out and go into the alveoli. So once again, the carbon dioxide that is dissolved in the alveoli, in the blood, that is going to diffuse into the alveoli. Easy. The carbon dioxide bound to the hemoglobin is going to dissociate due to the law of mass action at the site of the alveoli, and it's going to diffuse into the alveoli. However, what happened in the last step during the bicarbonate conversion, we are going to have a reverse chloride shift where bicarbonate is going to go back to the red blood cell and chlorine is going to leave. So what's going to happen then is the bicarbonate is going to react with a proton that is going to also be released by hemoglobin, and the equation is going to go into reverse. Bicarbonate plus the proton is going to equal carbon dioxide and water. The carbon dioxide can then diffuse out of the alveoli. This diagram is also 18.11. I definitely suggest you take a look at it and draw out this pathway so you understand what each part of the process means and the different ways that carbon dioxide is transported to be removed from the body. And that is all.